We've got maps for just about everything. Cities, oceans, even the stars. But what if I told you there's a map for everything, for matter itself, a guide to the very stuff that makes up our universe?
To see why this map is so incredibly important, let's take a little trip back in time. We're talking the 1700s. Imagine you're sick, you go to the doctor, and he hands you a pill of pure mercury. And the craziest part? Sometimes it actually worked. I mean, you'd be cured of whatever you had, but then you'd die from the mercury. Yikes.
So that brings up a really big question, right? How can the exact same thing be both a cure and a deadly poison? The answer, it turns out, isn't just about mercury. It's about finding these hidden rules that control all the elements.
And trust me, mercury isn't the only element with a wild backstory. The ancient Romans, for instance, had these bombs filled with bromine. When they went off, poof, a poisonous gas would just suffocate their enemies. It was a seriously brutal kind of chemical warfare, way before anyone had a clue about the actual chemistry.
And this is the whole point. Figuring out why these things behave so differently. Why one is this weird liquid metal and another is a deadly gas, it all comes down to that map I mentioned. The one, the only, periodic table of elements.
All right, so to actually use this map, we've got to learn how to read it. And I know at first glance it just looks like a bunch of boxes, a simple grid, but trust me, the way this thing is laid out, it's pure genius.
Basically, there are two main ways to look at it. First, you've got the vertical columns. We call these groups, or my favorite, families. And that's exactly what they are. Elements in the same family act alike. They have similar personalities. Then you have the horizontal rows, called periods. As you move across a row, you see these repeating, predictable patterns.
And if you look closer, each of these little squares is just jam-packed with info. Every element gets its own tile with its symbol, its atomic number, that's just the number of protons, and its atomic mass. It's kind of like a little passport for each element, telling you its vital stats. Okay, let's dive into some of those families we were talking about. Remember, these are the vertical columns that group elements with similar personalities. You've probably heard of some of these. Over on the far left, in Group 1, you've got the superreactive alkali metals. Right next door in Group 2 are the alkaline earth metals. Now, let's jump way over to the other side. Group 17, those are the halogens. And the very last column, Group 18, that's the noble gases. They're famous for being, not reactive at all. Oh, and that huge block of elements right in the middle? Yep, those are the transition metals. And this contrast is a perfect example of why these families are so important. Take the halogens in Group 17. They are so reactive, they're practically desperate to find a partner and bond with other elements. But then you look one column over at their neighbors, the noble gases, and they're the total opposite. They are super stable, kind of aloof. They really just prefer to keep to themselves. Okay, want to hear a fun little secret about the table's design? You see those two rows way down at the bottom, kind of floating on their own? Well, they don't actually belong there. They're supposed to be slotted right into the middle of the main table. So, why'd they get pulled out? No big scientific mystery. It's literally just so the whole chart can fit nicely on a regular sheet of paper. Kind of funny, right?
All right, so we've talked about the families, but there's an even bigger, more fundamental split that cuts right through the entire table.
If you look over on the right side of the table, you'll probably see this thick, zigzagging line that looks kind of like a staircase. Well, that's not just some random design choice. It's a really important border.
Here's the deal. Pretty much everything to the left of that staircase is a metal, and everything to the right is a nonmetal. Simple as that. And just knowing that tells you so much about how they'll act. Think of it this way. Metals are generally givers. They like to give away electrons, which gives them a positive charge. Nonmetals, on the other hand, are takers. They want to grab electrons, giving them a negative charge. So, you might be wondering, what about the elements that are sitting right on that staircase line? Well, we call those metalloids, and they're exactly what they sound like. They can't quite make up their minds. Sometimes they act like a metal, other times they act like a nonmetal. They're the fence-sitters of the periodic table. Now, with any good rule, there's always an exception, right? And the big one here is hydrogen. Look at it, sitting way over on the left in Group 1, hanging out with all the metals. But don't let its location fool you. Hydrogen is the ultimate rebel of the periodic table. It almost always acts like a non-metal. Okay, so we've got the layout, the families, the great metal divide, but the real magic of this table, its true genius, it's not just how it organizes stuff.
It's that it contains a hidden code. And this, right here, is the most important thing to understand. The periodic table isn't just a list. It's not just a catalog. It's a predictive tool. If you know an element's address on this map, you can actually predict how it's going to behave. It's incredible.
So let's crack this code. It's actually beautifully simple for the main groups. Look at group 1 again. Those elements almost always form a +1 charge. Group 2? Yep, a +2 charge. Now, we're going to skip over those messy transition metals for a second and jump to group 13. They form a +3. See the pattern? Now watch this. It flips. Group 15 forms a -3 charge. Group 16 is -2. Group 17 is -1. And what about group 18, the noble gases? A nice, stable 0.
And that right there, that's the superpower of the periodic table. An element's charge, that's everything. It's the key to who it'll be friends with, who it'll react with, what kinds of things it can build. Just by knowing where an element lives on this map, you know its deepest secret, how it's going to interact with everything else in the universe.
So we're back where we started. From those crazy mercury pills to modern chemistry, the periodic table is the map that makes sense of it all. It shows us the families, the patterns, the secret codes that run the whole show. And it really makes you wonder, doesn't it? If this one elegant chart, a chart designed just to fit on a piece of paper, can predict the fundamental behavior of matter, what other incredible secrets about our universe are just hiding in plain sight, waiting for us to find the right map?